Hey, so thanks for coming. I, I'm a security engineer at Google. Many years ago, it's good to be back in NUS. Many years ago, I used to be a member of core team. This was roughly 2015 in one of NUS Hackers' very early iterations. And it's truly delightful to see that NUS Hackers as an institution has persisted for the last 10 years. So after graduation, I moved to Seattle and I've been bouncing around a bunch of tech companies doing red teaming and penetration testing and eventually landed on Android's product security team. My team basically sits at the top of the vulnerability pipeline for Android. So we see bugs and reports from a bunch of sources from, internal bugs found by software engineers, our internal red teams and penetration testers. We also get a lot of bug bounty submissions, and the more interesting things would be the more exotic sources like threat intel from Google's threat actors group and other NGOs. So in 2023, we got a report from a brand new researcher in our bug bounty program. It seemed quite absurd at first glance. The researcher claimed to be able to uncrop a screenshot that you had previously cropped and saved. We now know this as the Acropolis bug, and it was severe enough that it actually made headlines in mainstream news. So here's what it looked like in practice. You start with a screenshot, and then you crop the screenshot. But then somehow, if you ran it through the researcher's technique, you got to recover most of the original image that contained stuff that you thought you had removed. How did this work? So there's three parts of this story. The first part is about file modes. So in a typical programming language, when you open a file, you open it in truncate mode. The contents of the file are cleared, and then you start writing fresh content from byte zero. In Acropolis, the screenshot actually opened the file in append mode. And when you crop an image, you're going to end up with something that is smaller than what you started with. So when you're overwriting the same file, the initial bits of it are going to get overwritten, but there's going to be a bunch of garbage at the end of it. The second part is file formats. So some file formats are strict. Think about JSON, right? If you have a JSON blob and you have some garbage at the end of it, your parser is most likely going to throw an exception and you're going to find out immediately. PNG is a bit different. PNG is lenient. Any garbage at the end is simply ignored. And this is the reason why the bug went undetected for so long, despite automated testing and despite actual real-world usage. The most important part of the story is where the mistake was made. Like opening a file in append versus truncate is a plausible error, but that's not actually what happened. So when we investigated, the app did everything correctly. The code that did the file I/O was actually existed since the beginning of the app, and nothing changed. It was correct when it was written. So here's why it really happened. Somewhere around Android 10, there was some refactoring, and that refactoring had inadvertently changed the default mode from truncate to append. So now the code that was once working correctly, it's now a serious vulnerability. And you can imagine the scope of the problem. If you're cropping a screenshot and editing it, you're most likely gonna send it to someone else. And now it's out of your control. So there's a whole corpus of screenshots floating around the internet with some data that people thought they removed. And that's obviously not great. This platform change happened many years ago, and like today, obviously, we are way more deliberate in making behavioral changes to avoid precisely this kind of problems. So that brings us to the topic today, which is OS and platform security. Your app can do everything right, but it is ultimately the operating system that underwrites all of the promises you're making. When people talk about Android security, typically they're referring to application security. So the concern here is securing one app against another app, or maybe securing the web service against a potentially malicious app, or sometimes just trying to make it difficult to extract the intellectual property in an app. If you're interested in AppSec, we actually collaborated with Hextree. They published a full Android application security course. It's on the link, and I think the talk is recorded, so like you can look it up later. Platform security focuses on the OS itself. We want to be resilient against apps that are on the device, but we also need to be resilient against external threats to the device itself. So this is a broad and deep topic, and the goal here is not to be a fire hose. So I think the main takeaways here are basically giving you the tools and mental models to understand platform security and to for any given piece of code to figure out where it fits in the bigger picture. So before we continue, like what exactly is Android and what is this platform that we're talking about? It seems like a simple question, but it's actually a pretty complicated answer. So all of this is the shape of the Android ecosystem. Let's break it down slowly. So we start with Google and the Android open source project, and I'll use AOSP and Android kind of interchangeably here. Android is not Google, and we are very deliberate about drawing a clear line between the two entities. You might know that Android is built on top of the Linux kernel. The way we do this is we ship a generic kernel image that OEMs can modify. So that brings us to device OEMs. Uh, OEMs take AOSP and they modify it to add their own unique flavor to Android. The end product is going to be a physical device, so there's going to be some hardware involved. We need drivers to run that hardware, and OEMs get those drivers from the respective vendors. They bundle that into the firmware image. At this point, you have kind of a bare bones Android operating system, but that's still not the experience that you're used to. So OEMs also add in like first-party apps and some higher level customization. If you bought an Android device, there's a good chance it comes with Google apps preloaded. So Google apps are made by Google, they're signed by Google. We give them to OEMs, and then they bundle that into the firmware. If we're talking about a phone, then the ISP or the carrier also comes into the picture. The OEM needs to work with every single carrier in every single market to do compatibility testing, to figure out the network configuration, and generally get approval to sell the device. Some carriers are also going to require that carrier-specific apps get preloaded. Every carrier has their own requirements. So, if you are selling a device in a broad range of markets, that can get very complicated and very expensive quickly. On non-pixel devices, like some OEMs decide to preload third-party apps. The goal is to give you a better out-of-the-box experience. So after all this customization, like what makes the operating system still Android? So there's a list of specs and requirements called the compatibility definition document, and it is backed up by a corresponding set of automated and somewhat manual tests. OEMs will run the firmware image through this compatibility test suite, and if it passes, then we certify it and it's Android. Up to this point, we're talking about pure software, but it still needs to somehow turn into a physical thing that you can buy and take home. So the physical supply chain is incredibly complex as well, and we're not going to go into it. But the gist of it is OEMs take the firmware image, it is sent to some abstract notion of a factory, and it ends up on a device. The device finally gets a signing key from Google again, and this forms the root of trust for direct boot. Sorry, for verified boot. And so the sum of all these moving parts is what you would recognize as an Android device. And then, of course, at this point, you start installing apps and using the device. So coming from a security perspective, you might already be thinking about all the ways that you can attack the ecosystem as a whole or piecemeal through each of these relationships. And you're absolutely correct. My wider organization is concerned with securing the entire ecosystem, and across the various teams, we have people working on securing each of these relationships. Platform security is just this bit of Android that focuses on AOSP itself. So when I think about Android security, there's two main views of it. There's the top-down view of the UX principles that we want to achieve and the physical device itself. And then there's also the bottom-up view of the architecture that the OS uses to underwrite these promises. Let's start with the top-down view because that's more tangible, I guess. Android is built around the concept of multi-party consent. So there are 3 to 4 parties in the model, and every party must consent before an action is allowed to happen. Starts with the human user, which is the real person who's actually using the device. Unlike desktop operating systems, the app developer is also a party to the consent model. Developers get a say in how their app is going to get used. This can be aggravating. You bought the phone and you want to use it however you feel like. The long story short is that a lot of mobile experiences, things like banking and video streaming, these are only possible because we can assure developers that their content can't be trivially stolen or abused. The third party is the operating system, and the operating system brings these things together by enforcing the consent model and making sure that apps require permissions in order to access device functionality. Developers can have opinions about how their app is going to be used, but fundamentally, apps are still constrained by what you have consented to. Android tries to make sure that it is explicit consent and it's also informed consent. And we are opinionated and try to steer users to make secure choices. The final party is something that you might not encounter in your day-to-day life, the enterprise. If you got your phone from a company, you don't own the device. The company owns the device. And there's a concept of a device administrator or a device owner who can set policies on the device. The one thing that Android does differently here is we only allow device policies that make the device more secure, never less secure. So what does consent mean? Somehow we need to prove that you are legitimately interacting with the device. And so this is authentication. The lock screen that you might see referred to as key guard is the main security boundary that people interact with. Authentication basically means you unlock your phone, you pass a key guard check. Android's lock screen has two main kinds of factors. The first is a knowledge factor, something you know, so like a PIN, a password, or a pattern. And then there's biometrics, which are in something that's intrinsic to you. Which is better here? There's a classical argument that a knowledge factor is always better. Like one of the reasons is that you can always change your password, you can't change your fingerprint. Another reason is, biometrics are probabilistic. There's always going to be some kind of false acceptance rate. In practice, it's more complicated, right? It depends on the threat model. Knowledge factors are vulnerable to shoulder surfing. A common phone theft scheme involves two people working together. So one of them is going to create some pretext for you to unlock your phone. So they might be asking for directions or checking the time or getting you to share some photos at a bar. And then the other person is watching intently as you unlock your phone and while your attention is somewhere else. Once the pair has learned your password, they snatch your phone and they run. And now they have your knowledge factor, and because of that, they have full access to the contents of your device. You get your account stolen, you get your bank accounts compromised, etc. I think this threat model is probably salient to most people, and if this is your main worry, biometrics here would be the better option. So Android's lock screen also has a unique attack surface you won't find on the other OS, right? We allow apps to draw content over the lock screen if they want to. This has legitimate users. Like the flag that controls this is show when locked, and this is the mechanism that things like your messaging app will use to draw the incoming call UI when you receive an incoming call. The problem here is that device security is effectively delegated to this app that has taken on the responsibility of the lock screen. If the app is well designed, it can do a good job. It takes care of your contents, but it's also possible for the app to just generally be more shoddy. It could do silly things like expose a web view with cookies, or it could expose a file picker that grants access to your device, and this effectively defeats the lock screen. So this touches on kind of an Android design philosophy. Android prefers to give users more control, but the trade-off here is that we're also creating more attack surface for people to make mistakes. And this design philosophy comes up in a bunch of places, including like side loading, which is why Android often comes up in conversations about scams and ransomware. So KeyGuard, the lock screen, it also plays an important role in the lifecycle of booting up a device. So the point at which a device is unlocked determines the the encryption keys that are in memory, and what data is effectively at rest. Modern Android devices use a scheme called file-based encryption. There was an older scheme called full disk encryption, but it's less secure and it's probably less relevant today. File-based encryption has two main buckets. There's device encrypted and credential encrypted. The device encrypted storage is intended for the minimum metadata needed to bring up your device. It is unlocked the moment you turn on your device, and it remains unlocked after that. The majority of your data is supposed to be in credential encrypted storage, and this is only unlocked the first time you unlock your phone. So there's two important things to call out here. There are two states. There's before first unlock and after first unlock. And you'll find these terms frequently come up when you're discussing exploitation and digital forensics. So again, device encrypted storage is unlocked after booting up, but only device encrypted storage. Your data in credential encrypted storage, in principle, is still safe. So even if you had a sophisticated exploit that gives you code execution, before first unlock, it's not going to get any of your data. After the first time you unlock your device, the credential encrypted partition is unlocked, and it remains unlocked for the rest of the device's uptime. At this point, that same exploit is going to expose the full contents of your device. So a key insight here, if you think you're in a sketchy situation and you think you might be at risk of one of these sophisticated attackers, the best thing you can do is to reboot your device to put it back into BFU state. Now, obviously, this is not going to prevent someone from simply forcing you to unlock it, but it's also going to make sure that you have to be complicit and you're aware that someone is unlocking a device and you have to be complicit in it. So that's a top-down view of device security, and it's also how an end user is going to experience Android security. If you're doing security research, you must also consider the bottom-up view of the technical measures that we use to underwrite all of these promises. So I'm going to try and skim through the Linux details. I think the main goal here is, again, to give you the vocabulary that you can look up later. So in terms of the security model, the process is the smallest unit of isolation. Code running within a process is free to do whatever it wants, and there is no meaningful way to isolate data or code within that same process. In particular, like there's a class in Java called the security manager. Well, that is not a strong security boundary. There's a best effort sort of thing. Don't rely on security manager to isolate code. Another kind of anti-pattern that we've seen is app developers and platform developers trying to isolate code by extracting it into a native code binary. That is also not a security boundary. It doesn't work. If you want to isolate code or data, it needs to be in a completely separate process. And Android has a thing called isolated process that lets you do that. So processes exist within the context of an app. On Android, every app is an identity principal. How this works in practice is that it gets its own Linux user ID when you install it. The next app that you install gets the next user ID, and so on and so forth. These user IDs are monotonically increasing for the duration of the device's uptime. So, if you uninstall an app, that UID is not supposed to get reused until you reboot your device. If it does get reused, now that's a serious security bug. A lot of parts of the operating system have non-persistent caches, and the underlying assumption is that UIDs don't get reused. So if you find a way to reuse a UID, you get all sorts of weird shenanigans, like you inherit permissions from the old app, etc. And that's a huge problem. Apps need to talk to each other, and the canonical way to do this is using a component called binder. The binder is implemented as a kernel driver. If you cut through all of the abstractions, IPC involves making syscalls like ioctls to the binder device. You never have to do this in practice. You would instead use a higher level abstraction like an intent or a service or a broadcast. Now, if you're not familiar with Android development, one of the simplest ways to talk to another app is to create a message called an intent. There are some kinds of intents that are called implicit intents. These don't have to specify a destination explicitly. What the intent does is it describes the capabilities that an app would need to handle it. And then apps that want to handle such messages correspondingly define those capabilities in what's called an intent filter. So how does Android look up these intent filters and then route your intent to the right receiver, the right destination? The code that does this is in a component called Activity Manager Service, and it runs in something called System Server. System Server is a large set of services, and among other things, it manages permissions, notifications, external storage, telephony, Bluetooth, a whole bunch of stuff. The functionality in System Server and other privileged services is is one of the things that turns a Linux distribution into Android. And accordingly, if you're looking at platform security, this is also where the vast majority of bugs are going to be found. As an Android app developer, you would use a set of APIs that you might loosely call the Android framework to interact with the phone itself. The logic behind these framework APIs is always divided into an app side component that runs in the context of your app and a backing system service. The app side component might do some sanity checks, but ultimately it has to bind to the system service in order to do most of its business logic and enforce security boundaries. The reason is because processors, again, are the basic unit of isolation. Breaking from this pattern is a common cause of security bugs. If you do a security relevant check in the app side of the service, a malicious app can bypass it quite simply by binding directly to the system service and making that call directly. So in the web context, we would call this kind of bug a client-side validation bug. The last concept of the bottom-up view is Android users, and this is really where the bottom-up meets the top-down view. Sharing devices among a group of people is actually quite a common user story in some markets, and users as a feature tries to support this use case. The same device security concepts apply to Android users. Each user has its own lock screen. Each user has a credential encrypted partition, device encrypted partition, and users also exist in before first unlock and after first unlock state. Once a user is unlocked, it just remains unlocked for the rest of the uptime. Rebooting the device is currently the only way to put data back at rest. Android doesn't have a logout button. The key thing here is that users are purely system server level abstraction. You can think of users as logical groups of apps, and remember that apps are already isolated from each other. Under the hood, they are just implemented as ranges of Linux user IDs, and every system API needs to do its own checks to make sure that it is not breaking isolation between users. This abstraction breaks down the closer we get to hardware. Generally, there's only one set of hardware, that's your device, and that hardware can be atomic. You can't partition it any further. So the clearest example is a SIM card that's associated with a phone number, and your device has one SIM card, has one phone number, regardless of which Android user is currently active. If you get a one-time password, it's just going to show up in the Android user that's currently in the foreground. So this bottom-up view is the architectural template of every single OS feature. If it needs to isolate risky code, it would have an isolated process. Every framework API is going to have an app side component and a system service side component. And it must always do the bulk of its business logic in the system service, otherwise it can be easily bypassed. Those services need to be aware that multiple users are a thing, and then they need to take care to not break isolation. So with that in mind, I think that's enough context to talk about what's interesting in Android right now. When we were talking about Android users, like again, every single system API needs to do its own checks. So you might be starting to guess at the problem. There are hundreds of APIs, and in a software system as large as Android, there are going to be mistakes. Three common modes of failure here. The most common problem is just forgetting that multi-users exist and not doing those checks. multi-user Android was not Android. The initial version of Android was single user. Multi-user was a feature that was added on along the way. So some of these APIs just simply predated the feature and weren't updated, and then we get a bug report about them. In less common cases, we might incorrectly trust the caller of an API to be honest about its identity, or we might take some data from a caller and then write it to a file and then asynchronously read the file later. And then by the time we read the file later, we've lost the notion of who wrote that data in the first place. So this report from last year is a good example of misplaced trust in the caller. It involves two Android users on the device. We have the victim user that we will call Alice, and then the bad actor that we'll call Mallory. So Mallory installs this malicious app on the device with the goal of trying to grab a picture from Alice. To trigger it, Mallory uses a system app, the settings app. So Mallory says, "Hey, tells the settings app, the picture I want is in this bad app, and please go fetch it from there." Bad app returns a content URI, but instead of the stuff after the stuff before the add is actually the Android user ID. But instead of using Mallory's own user ID, it uses Alice's user ID. Now, because it's a system level abstractions, one of the side effects is that something like settings does actually have access to Alice's picture. So it happily loads Alice's picture and gives it back to the bad app, and Mallory gets to see it. The bug here is that settings access the file using its own permissions and contexts rather than trying to check if Mallory actually had permissions. And that's also the fix. The settings app should always check that the caller has permissions and not simply use its own. This is basically a textbook confused deputy style vulnerability. So one of the most exciting things about working on my team is that we sometimes get to interact with vulnerabilities of public interest. Phones accumulate a lot of very valuable personal data and transitive access to other areas of your life. And there is a lot of interest in gaining access to a locked device, both from the criminal angle, from the state-sponsored angle, and everything in between. When you think about the phone form factor, the most reliable way that you can interact with the device is actually the USB port. So here are some ways that the USB stack is exposed in an attacker. There is code that's running before Android boots up. So we have the chipset recovery modes that are specific to the processor that your phone runs. And then we have fast boot, which is a protocol that allows you to talk to the bootloader, and bootloader is device specific as well. Then we get to the Linux kernel. After booting up, we have the device driver for the USB chipset itself. Modern USB is complex. Something as deceptively simple as fast charging your phone actually involves a software protocol to negotiate current and voltage. On top of the chipset, we have a large number of peripheral drivers. These things, they support the random gizmos that you might one day plug into your phone. All of this runs in kernel space. So if you have a memory safety style bug or any other kind of bug, it's going to give you privileged code execution. Then we move to user space. We have application level protocols. Like if you plug in a phone to a computer, you might be able to emulate mass storage, or you might do MTP or PTP. And then you have things like Android Auto and the Android Open Accessory Protocol. So attacks against these things usually don't care whether your phone is locked or unlocked, with the exception of whether it's BFU or AFU. But let's say you can determine that a device is already unlocked. What can you do? Even if you're not exploiting technical bugs, there's another tricky class of vulnerabilities that involves just emulating a USB keyboard and a mouse, and then you're injecting tabs and spaces to interact with UI elements and do something. At Black Hat, yesterday actually, someone demonstrated just such an attack. And in practice, you can get it to such a quick speed that all the user notices is a momentary flashing of the screen. And between Android and Google Pixel, we've actually fixed bugs, everywhere in this stack, up and down the stack. So let's look at one of them. This is a real bug in the USB stack. It was part of an exploit chain that was used by a threat actor targeting specific individuals. This is, it's kind of the same kind of bug like Heartbleed, if you remember that from many years ago. When you plug in a USB device, like one of the things that the kernel needs to do is to figure out what kind of device it is and what driver it needs to load. It does this by querying what's called the USB descriptor. It gets a product ID and a vendor ID, and it uses this in a giant lookup table to figure out the driver. This bug affects the HID, which is human interface device, and it's a multi-touch driver. So somewhere in initialization, the driver is going to allocate a bunch of memory using a function called kmalloc. And this is important because in kernel space, you don't get a buffer full of zeros. Kmalloc does not zero initialize. The HID driver then is going to call HID hardware raw request. And what this does is it just talks to the USB device and it asks it for some data. The USB device replies with some data. And that's the problem. The USB device has told the driver how much memory to allocate, but it also gets to control how much data it actually returns. So if the data received is less than the length of the allocation, then the remainder of the buffer is just going to contain uninitialized kernel memory. The whole buffer gets processed further by the driver, but is ultimately reflected back to the USB device. So that uninitialized data that could contain like pointers, kernel addresses, it gets leaked back to the USB device. And in the full exploit chain, those addresses are used in a subsequent primitive that eventually leads to privileged code execution on the Android device. So what's the fix here? It's literally one letter, like use kzalloc, that zero initializes your buffer. So now the USB device doesn't get any interesting data. And so that's quite a butterfly effect, right? Like it's literally a single letter change in the source code, but it created a vulnerability. It formed a key part of an exploit chain that ultimately put a real human at serious risk. But for such an impactful bug, if you look up CVSS, it gets ridiculous. It gets 5.5 upon 10. It's a very low score. Why is that? A large part of that is because of physical access. In I guess classic classic textbooks, physical access just drops the severity. The assumption is it's difficult. That mobile form factors are different though. Like physical access can actually be a far lower bar than remote access. Like consider how difficult it would be for someone to get network access to any of your computers, right? Like we'd have to compromise the NUS network. It takes a whole bunch of effort. What about physical access? Well, you just grab a laptop and run. That's it. So we can't rely on things like CVSS for mobile form factors. And in Android, we think about things from first principles, and we consider these non-invasive physical attacks just as important as the classic remote attacks. So what's even better than taking a laptop and running? Just sitting somewhere with a radio. Your phone contains a whole bunch of radios. One of the key things is a modem. Now, you probably understand that the phone is a general computing device, and that's an accurate mental model. But I want to extend that perspective by saying that it's not just a general computing device, it's actually a constellation of tightly coupled computers that are in the same physical form factor. So when you buy a phone, you look at things like the processor, RAM, storage. That's what we call the application processor. It's CPU, RAM, storage. That runs Android, it runs a Linux kernel. On a Pixel device, that's going to be one of the Google Tensor chips. Your phone also has a hardware security module. In fact, and this hardware security module is a separate, it's its own separate computer that runs a thin operating system, and it runs some code as well. In fact, like earlier I said that the lock screen is backed by a hardware security module. The component in the HSM is called KeyMint. And it's a program that runs on this separate operating system. Now, the hardware security module is supposed to be more secure, so the threat model is a bit different. The main so-called other computer that's residing on your phone is called the baseband or the modem. It also has its own separate CPU, RAM, and storage. It runs and that operating system and its code is just dedicated to processing stuff on the mobile network. The important thing here is these are all pretty obscure components. There's not much incentive to do better. I don't think anyone here shops for their phone tries to ask what the baseband is. The security of basebands, the degree to which they are hardened, they vary very widely between vendors and manufacturers. Like all computers, you can compromise it. Unlike a traditional network, though, the baseband is very tightly coupled with the application processor, and we're very concerned about being able to move laterally from the baseband and then use access on the baseband to then run code in the application processor and get access to your data. But that's actually not all. Your phone has some ambient capabilities. Like if you put your phone on the table, it's probably displaying the clock. It might count your steps as you walk without it being on. So on some devices, this is handled by yet another computer that runs another OS, has its own RAM, but this one is designed for extra low power. And then we're talking about the latest devices. Some of them, like the iPhones and the Pixels, they talk to satellite networks. So the satellite networks, there's generally two ways to implement this. On Pixels, we use a satellite network that that runs on the same frequencies and protocols as cellular network. So it just switches modes between satellite and cellular. The other way you could do this is by having two different basebands. And two different basebands means, well, two different attack surfaces that that you can potentially exploit. Two different things that we need to secure. So those are the hot topics on Android. And I want to switch gears a bit and shamelessly plug our vulnerability reporting program. There are two main Android-focused VRPs. The first is Android and devices. That's what I run. We accept bugs against AOSP, Pixel, Google hardware products. And then the second is Google's mobile VRP. And that's, Google apps run on top of Android. And if you find a bug in one of those, it goes to Google to the mobile VRP. And then, of course, we have each of the Android vendors tends to have their own channels to report bugs that are specific to that hardware. What happens after you submit a report? Android's security lifecycle is quite different from a traditional web service, and even a client software like Microsoft Office. And this is because of the shape of the ecosystem. The first step in this process is triage. Like we need to figure out how important this vulnerability is. It's basically myself, a bunch of engineers on my team. We sit down and we discuss whether something is a bug and what the severity would be. And even at this point, there are a lot of hidden complications that might not be obvious. A small number of bugs are obvious errors, like the kmalloc bug. These are easy to fix. But security bugs tend to have relatively simple fixes, and the simplicity can hide like impactful behavioral decisions that can be felt across the ecosystem. One example is Acropolis. That's pretty much the worst case scenario when you make a behavioral change without due care. And this is why sometimes as a researcher, you might submit a bug and you think it's a few line fix, you read the source code, but it takes months and sometimes years to land. It's because a lot of the work is just figuring out how to land this in a way that doesn't blow up the ecosystem. On a web service, you fix a bug, you push a change, it goes live. That's it. Android does not ultimately ship the over-the-air updates to your individual devices. That's the responsibility of the device manufacturer. So the code change still needs to flow through that entire ecosystem. It gets made by Android engineers in AOSP, then it goes to the device OEM, they do a bunch of their magic on it, and then it goes to carrier certification, it goes back for Android certification, and after a while it finally lands on your device. This takes a lot of time. That's why there's sometimes a patch gap. But for you as the researcher, though, it's far simpler. You submit a bug, it qualifies for the VRP, and you get your reward. And great, you've made a contribution. Android runs on more than 1 billion devices, and anything times 1 billion is kind of a big impact. So how do you get started? Bug bounty and vulnerability reporting programs, they are just a legitimate place for you to send your security research. You could drop a 0 day on the internet and you get a bunch of companies unhappy with you. You could sell it to the highest bidder and you get a bunch of governments unhappy with you. Or you could just do responsible disclosure. In my experience, there are things that predict success in this space. Right? The first thing is principles. Every software product is a hardware product also is built around a set of security principles and a design philosophy. On Android, the key principle here is multi-party consent. So try to understand a feature that you're looking at through this lens in relation to what the marketing has claimed that it does and in relation to the user experience on the device itself. The second is abstractions. In one of the first lessons in software engineering, you take a bunch of complexity, you wrap it in an abstraction like a function or a class, and then you forget it exists. Well, when you're thinking about security, the bugs almost always occur in the boundaries between abstractions where the assumptions don't quite line up. So it really helps to have a full stack view of this complexity rather than focusing on the single layer that you're working at. And then we have documentation. And without exception, documentation is always a lie, right? By definition, documentation describes the software's behavior as someone understands it. It doesn't describe the actual behavior. Sometimes it, by coincidence it does, but the source of truth is always the code. So, go to definition in your IDE is your best friend here. Even if it's a kernel function, figure out how it's implemented because, well, kernel bugs exist. And then the last thing is adversarial mindset. And this is probably the most nebulous thing. You've probably heard it a lot, but what exactly does it mean, right? So think of the adversary as your counterpart team of software engineers. They are also building a product, except for your bugs and vulnerabilities are their APIs and frameworks. And they're building a product to realize some kind of value. So put yourself in the shoes of the product manager, right? How, given this set of capabilities exposed by bugs and vulns, like how are you going to derive value? Are you after financial gain? Are you looking to, disrupt critical infrastructure? What exactly are you trying to do? And the way that you answer that question is really the user impact. And that user impact is the main thing that we focus on when we are deciding on how important a bug is. And yeah, and I guess with that, that's Android security in a nutshell. And I'll hand the time back to.
Okay, thanks.